Hello. Welcome to our class again. Um, 1 minute. Okay. So, um, before the lecture, um, let me introduce our guest speaker next week. So, we have like 2 more classes left next week. So this is our originally like the last lecture that will fully be taught by me. So next week we'll have 2 guest speakers. The Monday we'll have Professor Tae-Hong Park here. So you can read more of their bio in these links. So yeah, he's a guest speaker in ICMC 2024. So this conference just happened early this month, and you can see he holds a degree from Dartmouth College, MA. So he's both a composer and an engineer, and he did his PhD at Princeton University. Uh, and he did a lot of things, in terms of DSP, and also he's a composer himself, and he's also a bassist. So I'll definitely give more introduction when he joins us the next Monday. But you can just read his introduction here. And he was a professor at NYU, New York University, and now he works as an associate professor and chair of the Department of Music at Purdue University. Okay. So next Wednesday we'll have Professor Shlomo Dubnov. So Shlomo Dubnov is one of our faculty at UCSD, and he's here like for almost like 20 years, serving as a faculty in the music department and also computer science department, okay, at UC San Diego. And this is his brief introduction, but I think this is actually like written like 20 years ago, and he didn't really like update this thing. But yeah, in this recent 10 or 20 years, he did a lot of research related to machine learning, neural networks, and also, I used both their books in our class as textbook or just pure reference. So the book by Professor Tae-Hong Park is used here. This introduction to DSP, computer musically speaking. This is written by Professor Tae-Hong Park in 2010. Yeah, if I remember it correctly. And this is a really good reference for our topic on this sound sampling, digitalization, and everything related to digital signal processing. For Professor Shlomo Dubnov, actually, I had the intention. So in our first class, I talked about the neural network and new music technology, right? New music technology. That's happened in recent years. But unfortunately, we don't have enough time to get to this topic. So this module actually becomes an additional module to this class. But I hope Professor Dubnov can talk a little bit about neural network and his work on this field. Okay, so in this link, this is a book newly actually written by, published by Professor Dubnov in 2023. Okay, so it's called Deep and Shallow. I mean, it's deep neural network and just shallow neural network. It's basically everything about machine learning. Machine learning in music and audio. Okay. And also this book actually includes many content, not only, machine learning, but also some basic of sound, music, and something else like music information, fully transformed, fully analysis also included. So yeah, and even like artificial musical brains. So this is a comprehensive book, covered many different topics in the field of music technology and music generation. Um, but it uses more like modern techniques like statistics, machine learning, and neural networks. Okay. So it's a brief introduction to our guest next week. And I will send an announcement to this also, and for people who probably like miss the recording, I will send an announcement to the class, and I really highly encourage you to participate in real time. So I hope you can just attend our lecture in real time so that you can listen to, not only listen to their talk, but also ask questions and communicate with the experts in our field, right? So I think they will give a kind of at most 1 hour talk, and after that, I will hold a kind of a session for questions, okay, for student questions, and I will also ask follow-up questions for them. So I hope you can probably prepare some question that you might have and you want to ask them. I mean, like uh anything, like also maybe some suggestions for your career path. I'm not sure. Yeah, like yeah, if you're interested in this field, you definitely should like ask their thoughts, and maybe they can give you some directions, like things like that. So uh so Professor Timo Parker will join us at 2 p.m. So at the beginning of lecture on Monday, he will join us, and yeah, I'm still not sure how long his guest lecture will be. So I think approximately maybe 2 hours. So he will give a talk like 30 minutes to 1 hour, and we will hold a session for questions. So like 1.5 hours and or at most 2 hours. And after that, yeah, I will continue with my lecturing on this topic, okay? Music, math, and mind. So something about auditory processing, psychoacoustics, yeah, etc. And Professor Shlomo Dubnov, because he is actually in Tokyo now, so you know the time difference, right? So that's and he because of this time difference, he won't be able to join us at the beginning of the class. So I think he will join us like 3 p.m. or a little bit later than 3 p.m. and then he will just lecture and talk until like nearly the end of the lecture. Yeah. So this is the plan for our next week. Okay. Any questions or anything you want to ask? Okay. So yeah, so as I mentioned in our last class, again, the references and the materials here in this module, I may not have time, so because next week I will only be left like 2 hours in total to do the lecture. So I don't think I will be able to cover everything here, but everything in this either in the videos or in the readings are valid references for your final project. So you can cite them as as the in-class source for your final paper. Okay, so there's no problem. Even if I don't cover those some of the readings or topics or videos here, yeah, you can always choose the content here as your in-class reference. Okay, so now let's continue with our lecturing. Okay, so I want to so last time we just talked about the music technology used in hip hop, but actually music technology is used in not all the music production, right? I use hip hop here because I taught this class and I am more like into hip hop. music. But because hip hop is now like mainstream music, I believe most of you more or less right listened to hip hop. So last time we talked about speeding up the recording creates this chipmunk effect. Okay, and when you're slowing down the recording, it kind of gives you this chopped and screwed technique, pioneered by DJ Screw. And also we talked about auto-tune. Actually, because this session is kind of ad hoc, because I intentionally want to talk about fully transform, but I just because I just went to this effect menu, right? In this Audacity, there are many kind of sound effect. So I just remember this part, and I think maybe I can expand more on this. It's more like applied music technology, and some of you might be like interested in those creative music production techniques. So for auto-tune, because I don't really have this, I didn't really prepare these parts, okay, this part of lecturing. So I'm not able to show you the details or how do you code the auto-tune. But I think you can find many resources online, I believe. And if and I also have a student who worked on this auto-tune project in my hip hop class. Okay, let me find this. Okay. I think, yeah, I showed this in our first lecture. Yeah, maybe I'm not going to play his project, but yeah. If you want to, you can find this in my Music 17 YouTube channel. But yeah, so I have some students working on in this project, but I don't have the programming at hand now. So we probably skip this part, and we just give a very shallow introduction to what is auto-tune and how it's applied in music industry. Okay. So I also mentioned spatial audio, like the sound localization, right, where the sound comes from, and then it can kind of creates this spatial feeling, right? You can record the position of the sound source. Therefore, you use this kind of pen, like left, center, right, and also some head-related transfer function. When you it's kind of it's mostly used in this virtual reality, right? VR. It's mostly used in VR because in VR it requires this immersive experience. So when you put your headphone on, you want to kind of immerse in this environment because it's VR and it's like, let's say you are in a room and what you are hearing, what you are feeling, not only through your touch, right, through your hands or through your tactile feelings, but also your auditory feelings. You kind of know like where is the sound source like exactly, which gives you a more realistic feeling of the environment. Okay. So this is something you can look up to if you are interested in VR. Okay, so they use a lot of this is actually head-related transfer function. Okay, HRTF functions. And also like yeah, if I have chance to teach this class again, I probably will talk more about this because when I prepare this course, prepare the materials, I didn't even thought about talking about sound effects. So I didn't really prepare these things like in more like nuances. But you can definitely look into those resources online. There's a lot of introductions, papers, even videos, resources online. So today we'll continue with this list, and we will talk about another technique called vocoder, okay, or it's called cross synthesis. The vocoder, so the general idea is to combine two sounds, okay. The general idea is to combine two sounds by spectrally shaping the first sound by the second one and preserving the pitch of the first sound. A variant and improvement are the removal of the spectral envelope of the initial sound, also called whitening, before filtering with the spectral envelope of the second one. So what does it mean, right? So actually, vocoder or cross synthesis traditionally is how do you kind of change the quality of your voice, right? So the main source will be your voice or your the recording of some scene or speech, something like that. And the second sound will be some instrument like violin, guitar, or and other instruments or other kind of noise, any kind of source that you want use this source to modulate your voice. Okay. So spectrally shaping, it requires you to go to this frequency domain, right? Then you use the spectrum of your second sound to to spectrally shaping or modulating your original voice using that spectrum. So this process will preserve the original pitch or the original kind of the feeling, this how to describe this. So you can kind of recognize your voice, but it's through a different kind of timbre, right? Different timbre, different spectrum. So this is a very engineering kind of definition. So the sound effect can be demonstrated in this part.
Territory with a really interesting counter melody. Now, the first thing you hear is that solo piano melody introduced at the very beginning of the song. It's super, super memorable. And then you hear Kanye's voice. But it's processed through a vocoder to sound like a distorted guitar. Now, he could have easily disguised that vocal completely, but instead, he chose to reveal that it was his voice by seemingly testing it out before diving into the counter melody. According to Rolling Stone, there's no way it should work, but it keeps rolling for 3 more minutes without breaking a spell.
Okay, so in this video, so Kanye
territory. What you hear is
okay.
That solo piano memorable, and then you hear a vocoder to sound like a distorted guitar. To sound like a and then you hear Kanye's voice. But it's
right. So you hear this voice, right? So this voice is actually processed using this vocoder, and the two sounds, right? The first sound is his voice, and the second sound is this distorted guitar, and he used this spectrum of this guitar to shape his voice, which creates this sound, which is this vocoder. You see. I use a vocoder to encrypt a voice message. Interesting. But this is actually distortion, right? If you mean encrypt, you want to decode that, right? You want to encode the voice and you want to decode. So you want no information loss during this process in order to recover your voice, right? But in this processing, actually, it's kind of yeah, it's not a kind of it's not a lossless process, which means your purpose is to distort your voice to something else. So you don't care like if you can recover your voice from that modulated signal. Okay. So you may you can hide some of the characteristics of your voice, right, to make it undistinguishable from the original one, and this can kind of disguise your original speech or your original kind of alliteration, but the original pronunciation. But the problem is that because you don't care about how you recover that voice, so if you want to do this encoding decoding thing, it's usually not carried through a vocoder. Okay. Okay. So for the vocoder, I want to kind of dive in this topic. Actually, if you really want to work on a vocoder, the best way is to program, okay, is to prototype something using this principle, okay? So either in like MATLAB or some other programming language, is you do this by yourself. But since I don't really did this project myself before, and I also don't want to introduce you to complicated concept in terms of, kind of spectrogram, spectral shaping, and spectral envelope, and all kinds of these technical details. What we will do is we will cut a short path to vocoder is using this Audacity. So in Audacity, if you go to effect, there is something called vocoder. So on my computer, it is in Chinese because my system language is Chinese. Even if I change this to English, change my preference to English, I don't know why something still remains in Chinese. But whatever, you can easily find this in your own computer, in your own version of Audacity. Okay, it's called vocoder. Okay, this is something called vocoder under effect. And these are some of the parameters this vocoder application encodes. And if you want to know what these numbers mean and how do you manipulate this, there are two ways. One way is just to experiment, right? You just take some piece of audio and you just play with these parameters and see what kind of effect it produces. Kind of, it's kind of like by experimenting things and you have a feeling like what that means. And a better way is to just look into the menu, right? Looking through the menu. Well, it's in help menu, and then you can go to effects here and you can find all kinds of different effects. Vocoder is here. Okay, so you can see the same interface and it gives you different parameters, and there will be a lot of instructions, explanations for what all these parameters mean. Okay, and how do you use this effect. So I want to create some effects using this kind of device, this little device. So what I will do, again, like what we did in our last class, I recorded a piece of my own voice. Okay. This is music 7. So you can see, you can listen okay, let me do this again. This is music 7. You can hear there's a lot of noise, right? This is because actually I recorded this used directly my computer speaker. I didn't use any microphone. Okay, so when I teach you, I actually have this little condenser microphone, which can collect my voice better and make you sound, more clearer of my voice and less noise. But here, this one is recorded without microphone, so it's directly collected by the computer speaker, okay, computer microphone. And also, I recorded this in my office yesterday, where there is this kind of fan noises, this kind of air circulating system noise in the background. So I'll play this again. This is music 7. Okay, so there's a lot of noise. So I will today I will continue with this list, okay, of effects. Last time we talked about volume, amplification, how to adjust the volume level. So this is very straightforward, right? Just adjusting the amplitude, like how large this kind of waves are, okay, the amplitude of the waves. So I'm not going to repeat those things, and we also talk about feed in, feed out, and something about pitch and tempo, and we just expand this to this hip hop and music production. So today we will cover all those sound effects left. But now, because we already encountered this problem of noise, right? Then I want to talk about this thing first. It's called noise removal. So in Audacity, there is an algorithm to remove this noise. So this algorithm is some engineering solutions. So simply speaking, it uses this autocorrelation sequence. Okay, it computes this autocorrelation. So how this works? So if you go to this noise reduction, okay, it gives you, it tells you what to do. So step 1 is to select a few seconds of just noise, so Audacity knows what to filter out. Then click Get Noise Profile. Step 2, select all of the audio you want to filter, choose how much noise you want filtered out, and then click OK to reduce noise. So this process includes 2 steps, right? So first, you need to know what noise you have, and then you just tell the program, okay, this is a noise I have. I want you to remove everything similar to this in my recording. Okay. So how this works? So yeah, simply speaking. So for example, I know in my recording this part is the noise. Okay, let me play this. Right, so this is noise, and this also at the end is the noise. Right, they sound similar. They sound similar, like this kind of like this white noise, something like that. Okay, let me do a kind of profile. Let me analyze this and plot spectrogram. Okay, not enough data. Okay, so yeah, this is a very rough, not accurate representation of the frequencies, but it's something like this. So if you hear this voice or this noise, right, it somehow presents in all my in my entire recording. Okay, this is music 7. So this kind of like white noise continuous appears in my background of this, and when I choose this part and I say, okay, go to effects, noise reduction, get noise profile. So it gets the noise profile. Okay, and now if I need to select all my recording and go to effect and noise reduction. Let's use the default. Okay, noise reduction dB is 6 dB sensitivity, frequency noise. Okay, let me click this OK. Okay, so you can see these parts, it becomes much more like flattened. Let me hear this part. Right, this is a little bit of noise. And what if I play my video or my recording? This is music 7. Okay, so let me make a copy of this. Okay, so that's so that you can compare the difference like between and after the noise reduction. So this is the original one. Let me see. Okay, let me get the noise reduction, get noise profile, and effect. So let's use the defaults for now. Okay. Now let me play this first original one. This is music 7. Let me play the next one. This is music 7. Right? You can hear obvious kind of noise removal effect there. So okay. So let me do this again and try another kind of another parameters. Okay, get noise profile, select effect. So here you can see this noise reduction is 6 dB. Okay, it means I only reduce 6 dB of my noise. So there's still some noise presented in my recording, right? So this is reduced noise, and if you hear this part, right, there's still some noise. It's quieter than this one. Sorry, I need to do this. Right, it's quieter than the previous one, but it's still presented. Let's see. What if you want to reduce all of those things, and then you can increase this parameter, right? And you can see this kind of the wave becomes the gain is reduced, but this becomes more flat. It becomes more flat. Let me play this one. So now you can barely hear the initial noise. Okay, let me play this entire recording.
This is music 7. This is music 7.
Right? It becomes much quieter, like in terms of background noise. So the noise basically out of the recording now. Okay, so let's see. So then you probably think like, if I have this tool, like why I don't reduce all of the noise, right? Why the default gives me 6? Why it only reduce part of the noise but not all of that? Maybe let's try with a much larger parameter. Let's see. Okay, let me play this.
This is music 7. This is music 7.
Okay, compared to the original one.
This is music 7.
So actually, I don't know if you can hear this or not. But actually there will be certain of some distortion, okay, in this noise reduction process. So now when I'm using this extremely large noise reduction level, you can see this part, right? It's almost flat. Okay. So let me take this part, and you can compare these two lines. So you can see the second line is almost silence. So silence means just straight line at 0. But here you can see more of these vibrations probably. So there will be distortion, simply speaking. If you use this program to do this noise reduction, it doesn't mean the larger the better. The larger the parameters is, the better the result will be. So if you use this large kind of noise reduction level, your original recordings, means your sound will be somehow distorted because you are reducing too much of the content in this recording, and also in the same time, not only the noise, but some characteristics, some perspectives of your original recording will be will also be eliminated. Okay, which will cause some sort of distortion in your original recording. That's why you need to find this kind of middle ground where you can reduce some of the noise you don't want, but you still preserve much of your much of the quality of your original recording. Okay. So for what parameter you should use, it's basically by experimentation, okay, and also your own personal preference. So I think in this case, maybe 12 will be something reasonable, right? Okay, now this, let me see. Effect. Okay, if I use 12, the noise is reduced, and I think the original recording should not be distorted that much.
This is music 7.
Okay. Comparing to the first one.
This is music 7.
So still some distortion, I believe, but not that much. But if you think, yeah, this audio also lost a lot of, some quality you want, you may increase. I mean, you can decrease the noise reduction level to preserve more noise and also more of the original quality. Okay. So this is the effect of noise reduction. Okay. So some click removal or noise repair. I'm not going to talk about this. Okay. So now let's continue with our topic. So now let's say I have this one, and I probably, let me get rid of the original recording. Okay, let's say, okay, now I have a noise reduced version of my voice, and I want to use this voice in my experiment. So if you remember, we are talking about this vocoder, right? So let me delete this first part. This. Okay, so vocoder. So in vocoder, you need two sources, right? First is the voice. Now we already have this voice. I record it. And what about the other modulating source or modulating signal? So here actually I collected some of these recordings. Okay, you can see there are different instruments and also some noise. Maybe let me try with this one first, this trumpet. Okay, let me solo this one. So this is a trumpet. Now I want to use this trumpet sound to modulate my voice, okay, to create a vocoder effect. So what I will do is that, first of all, I will make a stereo track, okay? So go here, click make stereo track, and yes, it doesn't matter. Now I have a stereo track, means I have left channel and right channel. My left channel is my voice. The right channel is the trumpet. Okay, if I play this sound now.
This is music 7.
Okay, so there are two separate sources. The left is voice, the right is trumpet. And now, if I select this clip and go to effect, go to vocoder. Okay, and let me use the default. And if I say I apply this, okay, and now I have a new recording. And let me play this sound. Right? You can hear this, right? You can have a feeling. So you can basically recognize my voice. This is music 7, but it's kind of distorted by this trumpet and make it sound like a like this robotic mechanic kind of feeling, like this in this sci-fi sci-fi movies. Yeah, something that these aliens will say, right? Let me play this again. So this is the effect of vocoder. Okay. Actually, you can use all different kinds of sources to modulate. Okay, let me see. Now let me choose another thing. What will I choose? Okay, I think there's also other things I want to talk about. But what about piano? Let me use this piano. So when I use this trumpet, you can see the trumpet recording is longer than my voice, right? So when I make these two tracks, one stereo track, actually I appended the end of my voice using this silence so that it's the same kind of, the same length. But now my piano sound is shorter than my voice. Let's hear the piano sound. Okay, so this is a piano. So it's much shorter than shorter than my voice. Okay, so actually I can do this. The original sound is actually very long. Okay, original sound is very long, but it's most silence. That's why I just truncate this. Okay, so let me just truncate this to the same length of my voice, and let's do the same thing. Okay, so same thing. Make it stereo. Okay, and then go to vocoder and apply this. Again, I don't know how do you feel about this sound. If you want to, you can comment in the chat. But I feel it's like less distinguishable than the trumpet one. The reason is that because we are not when we use the piano to modulate our voice, we are not only use the spectrum envelope, we're also using the amplitude envelope. So the amplitude envelope means, right, in this track, this piano is a kind of diminishing sound. It's decays pretty rapidly. And then when we use this quickly diminishing sound to modulate our voice will also diminish, okay, very quickly. That's why when I talk about this is music 7, then you will see you will hear this is kind of loud, but music 7 become much quieter here. And this probably this is not something we want, because we want the voice to be modulated but not become quieter and quieter. We want this sound to be at the same level but have the quality of the piano. Then what you can do for a sound like this, right? Now I will introduce another effect. Okay, so in piano, if I put it in this view, you can see mostly the existence of the sound, okay, the majority, the substantial part of this sound is in this part, okay, but this is too short. If we use all of these recordings, you can see like nearly all these parts are too quiet, and our voice won't be even presented in this vocoder modulated signal. So what we want is that we want to take this part and to extend it, right, to make it longer so that it can cover this whole period of my voice, so that I'm using this stable signal to modulating all my voice, all my my voice recording. Let's see, we pick this part and we just truncate this, okay? And this is too short. So how do you extend a recording by purely making it longer but not changing other characteristics? So in our last class, we talked about slowing down, right? Slow down the recording in the Houston hip hop pioneered by DJ Screw. But the problem of that operation is that, let's see, we change the speed, we make it lower. Okay, then it definitely becomes much longer. But if we listen to this, right, then the pitch is also changed. So when we're slowing down the recording, not only the audio will become longer, but the pitch will become lower. That's basic principle when we do this sampling kind of based audio processing. Then what we can do here is that we can use another effect. It's called pause stretch. Okay. Pause stretch is something means you purely stretch this audio, but you're not changing the pitch. I believe this is implemented. This is realized using this kind of spectrum analysis and spectrum manipulation of the audio. But now we are just using this very simple device to make it. So this is stretch factor means how long you want to stretch your recording. Okay, let's say we want this to be 3, which means 3 times the original length of the recording. Like this, okay, become much longer. Let's listen. Okay, so you can okay, so one thing I really need to do is to save the original recording, right? so that I don't need to okay, sample. Let me create another track, okay, and move the track up. And if I do this, and then I can listen to the original sound, and I can make a copy of this sound here. And then I can apply some effects so that we can compare the sound effect. Where is it? A pause stretch. Okay, 3 times of this becomes kind of 3 times longer, probably not really 3 times longer. But let's listen to this. Okay. The original recording. So you can hear at least the pitch is preserved, right? Although in this prolonged recording, there are so much nuances in the original recording, is amplified. Because this original recording is quick, then there are some, some vibration, some details, in this recording because it's too quick. So we just don't really grab those effects. But when we're slowing the recording down and we use kind of interpolation techniques, we are actually exaggerating or amplifying certain of these details of the audio to a larger scale. Then now we are listening to this much like vibrating sound. Okay, but the good thing is that although it doesn't sound as good as the original, first it preserves the pitch, and second you can tell the quality is still piano, right? You can still tell this is kind of sort of piano sound, but in real piano you cannot play a note in this quality this long. So but it's still like shorter than our voice, so let me prolong this little bit longer, maybe this time 1.5. okay, let's listen. Okay, so now we have two recordings of the same length. One is my voice, but another is piano. And now let me use the vocoder. Okay, make stereo track and select this, go to vocoder and apply. Okay, let's listen to this one. How do you feel? So it sounds like the piano, or at least sounds like the original, our processed piano recording, right? And you can still kind of tell my voice, the shape of my voice presenting there. Yeah.
This is music 7.
Okay. And mix stereo. And also, if you feel this effect is not obvious enough, you can actually change the parameters here. Okay. You can change the distance actually smaller so that the effect can be, so the voice, okay, the characteristics of the voice can be preserved more. Let's try this smaller number. Okay. So maybe my voice now present more in this precise signal. Okay, so this is another effect called pulse stretch. So we experimented this in our using the piano sound. So, and also we can just not only use the instrument, right? And there's also flute, violin. Maybe let's try flute. Okay, just do another experiment. Just for fun. See what flute will produce. Okay, this is a flute. Make stereo and vocoder it. Let's revert it larger. Apply. Okay, again. So now it use the quality of the flute to shape my voice. And here I also have a lot of other instruments that I downloaded. Okay, including the bell, the violin. Okay, the bell.
This
Maybe try this one. So I will share this file in our lecture files, okay, in that folder, so that you can experiment with all those instruments and the voice by yourself, and then it's also in your homework. So yeah, if you haven't submit your homework, you can also experiment with this effect. Okay, this is use bell. And also because the bell is also this kind of exponentially diminishing sound, that's why this effect is not really doesn't really apply very well to my voice, because if you use this kind of sound with this exponential envelope, then you can only hear the first maybe 2 syllables clearly, and everything else will be diminishing really fast, so that you cannot capture the original, meaning of the voice. But yeah, there's just some different kind of things you can experiment with, and also you can even experiment with the original voice. Okay, so this is my voice, and this is also my voice.
This is music 7.
Yeah, this is my voice with the noise, actually, the original recording, and this is the voice.
This is music 7.
Kind of processed after the noise reduction. So let's see, what if I use 2 voices, right? So what if I use the same recording to modulate each other? What the vocoder will produce? Okay, so let's just try it. Select, go to vocoder, and just apply. Let's see.
Music 7. Music 7.
Okay, so it doesn't really produce something good, because because there's some actually delay effect between the 2 sources. But this is also a kind of interesting thing that you can do, right? You can just delay your another source. It's 2 same recording, but you can delay another one a little bit, or modify another one a little bit, and then use this new source to be the second, the second recording, second sound to modulate your original sound. So here I believe there's still a little bit delay, or time difference here. But let's just see what kind of audio, what kind of effect it will produce. Okay, let me play this one.
This is music 7. This is music 7.
Okay, so it sounds with a little bit distortion, but it's pretty clear, pretty clear that what I'm talking about. And also you can see the noise here somehow disappeared. Yeah. This is probably because these 2 sounds are computed with autocorrelation. Therefore, only the correlated parts are preserved, and then therefore it kind of give you the same effect as noise reduction. But it's just my guess. Yeah, I didn't really have valid proof for this now. Yeah, and I need to look more into the details of how those algorithms are designed, how they really programmed yeah, this vocoder and noise reduction. Then I can draw this conclusion. But based on my preliminary assumption is that they kind of use the same autocorrelation principle. Therefore, because the noise are not autocorrelated, right? They are random. Therefore, they are kind of set off with each other in this process of doing this vocoder.
This is music 7.
So
This is
okay. So there are different sources, and you can use anything you want. Just be creative with yourself. I'm not that creative, but I think this basic principle is something I can explain well. And what else? So now we went through everything, basically everything in pitch and tempo. Okay, the sliding stretch is something you can experiment with yourself. I'm not going to talk about that everything in class. And the next is EQ and filters. Okay, this already talked about this, and delay and reverb. Distortion, wah-wah effect, any special, there's something. Okay, so there are a lot of sound effects, actually. So next, I want to talk about EQ and filters. Okay. So I think filter, EQ, is something that you will really encounter in music production or any DSP. Okay. So to talk about what is EQ and what these effects are, let me first talk about the noise. Okay. So there are different type of noises in Audacity you can generate. So we generated tune a lot. So here I want to talk about noise. So you can generate noise. There are 3 options: white noise, pink noise, Brownian noise. What's the difference? Okay. So here, first let me generate maybe from white noise. So I use a small amplitude, 0.1, and the duration is 3 seconds. So this is a white noise. Let me play this one. Okay, how that sounds like. Again, if I zoom in on this thing, then you can have a closer look into this white noise. Okay, so these points, right? They are very random. So white noise is just a random number generation. I mean, it follows some random process. Either it's pure random number, like of this equal interval between, like, minus 0.1 to 1, or it follows some Gaussian. Yeah, Gaussian functions. I don't know if it's, yeah, I'm not sure if the white noise here in Audacity is a Gaussian noise or just, random number noise. But it just follows some random process. Okay, some random numbers, random process, and generate something like this. Yeah, there's basically no no regularity, no rules. Wait. What I'm okay. So what I want to do is to do this. Maybe this one, maybe into this one. So you can see, this is my voice. Okay, so in my voice, you can see this kind of sinusoids or repeating cycles are happening, although they are not, pure tone, which means they are not, exactly the same thing repeating all the time. There are some modulations filtering in the process, but you can tell there is some, regular patterns here presenting that you can tell they are kind of, correlated with each other. But in noise, what is noise, right? Noise is something just using this random number generator, using some random functions, random process. I'm not sure. So most noise should be Gaussian noise. So it follows this Gaussian type of, distribution. But it's also maybe something of, from -1 to 1 of this equal. I don't remember the name of that distribution. Okay, so whatever. Yeah, sometimes it's just, yeah, the terminology just gets out of my mind. But noise, first is noise. So for the characteristics of noise, we are going to use this analyze plot spectrogram. Okay, so this is a really bad one. I also explained why this is a bad one, right? This uses too less window size. So if I use more of this size, you can have a better, more precise presentation of your noise. For example, I use this very large window size, and then you can see in the white noise, nearly all frequencies, okay, until the half of sampling rate, nearly all frequencies are presented equally. So they are basically of the same level with certain randomness here, but they are basically equally presented in white noise. So this is the frequency composition of the white noise. So every time you use this computer program generation white noise, it will generate something different. Okay, so they look the same, but if you use the okay, so you can see this shape here are kind of different, but the same thing is that they cover the full range of the frequencies, and the amplitude are basically the same. So the chances of all the frequencies are equally presented. Okay. So this is white noise. So since we're here, we can talk about, like, we can try what if I use a white noise to modulate my voice in this vocoder, right? Because you can basically use anything, any sound to make vocoder. So let's just try this out. Let me select this and generate, not an effect, vocoder. Let's apply. Okay. Wait, again. So if you use noise, it's more kind of intelligible than the instruments. Okay, so you can tell the voice components, they are better because the spectrum envelope of the noise, right, is just it's basically flat. So all the so the spectrum envelope of the noise here, right, is almost just kind of flat. It doesn't have a defining shape. It's unlike instruments. Therefore, most of my the frequencies in my original voice can be preserved better. So if you use some noise to modulate the voice, then your voice will be more kind of intelligible. So and also it adds some robotic effect and some like roughness, something I don't know how to describe this. But yeah, you can find some words of your own feelings of listening to this song, and you can try with different type of noise, different type of things. But let me recover this and continue our talk about noise. Okay. This is white noise. So let's generate another type of noise. What about pink noise? Okay. So you can see the shape is much different than this one, right? If we look into this more closely, so it's still random, but it's kind of I don't know how to describe this. It becomes smoother, right? the change becomes smoother and with more of this continuous type of feeling. And then if we look into the frequency component of the pink noise, you can see it's of this shape. So it's a low pass filter. With low pass filter, it means more of my lower frequencies are presented here. Okay, so in terms of my higher frequencies, larger than 1000 or 500 hertz, they are cut off. So therefore, it means in my pink noise, it's more of this lower frequencies, like the bass, booming part of your lower part, the lower part of the recording will be preserved, but the higher frequencies, the harsher one, will be removed, or at least cut off. So let's give a comparative listening to the white noise. This is white noise. This is the pink noise. So it seems this pink noise is quieter. Actually, it's not. It's not because it's quieter. It's because it cut off the higher frequencies. Therefore, more of the booming lower part are preserved. Okay. So what about another one? What about the Brownian noise? Okay. So with Brownian noise, you can see this is more like kind of like sawtooth type of thing. Okay, then you just so it actually becomes smoother even if you look into the details. But if you zoom out, it's actually more of these up and downs, like the sawtooth shape. I don't know if it's a good description. But if we will look into the spectrogram, right? So it's still a low pass filter, but it cut off quicker. Okay, it's cut off almost if you reach the 5000 hertz, it's almost zero already. So it starts this shelf from 30 hertz, 20 hertz even. Okay, and it's cut off quicker. And if you listen to the Brownian noise, okay, you can only hear the low frequencies. Okay, the pink noise, more higher frequencies are presented, right? So here you can see it starts cut off like near 100, and until even until 20,000, it's still frequencies presented there. If you listen to white noise, okay, like all the frequencies, lower, higher, whatever frequency are presented there. So yeah, all the frequencies are there. So these are different types of frequencies, and we just visualize their spectrograms, right? The spectral analysis. Okay, so just to do some experiment, maybe let me use pink noise to do this again. Yeah, I don't know. It's just some easy random experiment, and whatever sound you have, you just want to try it. Okay, let's listen to this one. This is music 7. This is music 7. Okay, it produces some different effect than the white noise. This is music 7. I would say more of the lower frequencies are preserved, but the higher frequencies in my voice are kind of filtered out. Change to this one. This Brownian noise.
This is music 7. This is music 7.
So it sounds more like the tremble, right? The lower kind of trembling, booming sounds are there. And it's because Brownian noise are basically all about the lower frequencies.
This is music 7.
So I think probably if you use some bass, some bass or even drum, I mean the low frequency instruments to modulate your voice, if you can do that, probably it will produce some sound effects like this. Like you are making your voice really low, really kind of, in these low frequencies, and I don't know.
This is music 7.
I mean, if you do music production, you may thought about something, somewhere this will be really useful when you view this spectrum, allocations, and really push those frequencies. And if you want to booming up, right, emphasize or booming your low frequencies, this might be something you can consider. Yeah. So whatever. So why am I talking about this noise? Okay, so let's go back to where we just started. I want to talk about the filters. Okay, equivalent filters. So how do you view the effect of equivalent filters? The best way is to find something of this unchangeable or just equal spectrogram, right? Like white noise, and then like our original spectrum is like this, and then we can just change this sound to any shape we want. So in this engineering, this is called whitening. Okay, you white some sound to a white noise, and which means you have this, this type of spectrogram, and then you can shape the sound from this stage to anything you want, you using filters. So let's try this. Okay, let's try this. Let's see this equivalent filter. So there are different types of things. Let's say we use this filter curve. Okay, so this is a shape I just did yesterday. Let's flatten this. And for example, here, I want to lower this down. Like 6 hertz, I lower this down. At 500 hertz, I booming this up. And near like 2000, 4000 hertz, yeah, I'm dragging this down again here. So this is my filter. So what this filter does to my sound will be, if I choose apply here, this is my white noise, right? Let's listen to this. And if we visualize spectrogram, right, it's exactly the same. It's, I mean, basically the same as what we just did in this EQ curve, right? I drag everything, so I cut off all the lower frequencies lower than 60, and from 60 I booming up 500 hertz here, and then near 4000, right, I started to just lower it down, making it flat. Wait, let me see if this. Right, so this is my EQ. Oh, this is the filter I designed. This is the real spectrogram I get. Okay, it's not precisely I mean, it's not exactly the same, because when you use filter, there are some function designing. Okay, and that filters cannot be like precisely reflect what you want. Okay, there is something in between in this change. Yeah, in this change, there's something of course approximations, because you are using these filters with pause, right? Then at this change point, everything have to be smooth. Okay, and you have to make sure your filter is finite filter, which means it won't explode. So whatever, there are some certain nuances there. Okay, it's not an easy process. It's not like, oh, I draw any shape and then my filter, my real spectrum can be of that shape. It's not like that. Okay, there is always some compromise you have to do in terms of filter designing. So everything will just cater to your needs, will approximate what you want, but it won't be exactly the same as what you draw in your in this EQ curve. Okay, so this different EQ, it's just different, different ways of representing this EQ. So this is called graphic EQ, where you can adjusting those things using this gliding glides, right? And things like this. But in curve EQ, it's more about this, continuous lines where you draw the points. But the working principle is the same. Yeah, the working principle is the same. So maybe let me reverse this thing back to white noise. And let me try this EQ, graphic EQ. Okay, so I'm just doing something random. I don't know what I'm doing here actually. And let's see what my resulting spectrum will be. Okay, so you can see now it's much less continuous, right? These different frequency bands. It's not as continuous as the previous one I used with the curves. But okay, let's see, this is the shape we want. And let's apply. And we go to analyze. Okay, so this is the real spectrogram I get by applying this this EQ. So let me go back here, right? You can compare these two graphs. Okay. So yeah, so it's definitely not a faithful reflection of this pattern I created here, right? It uses a lot of approximations and smoothing everything out. And the shape somehow, in this 250, it should slow down like this. And there's some, notch, notch and the crest, valleys, whatever. It somehow simulates what I created here, but it's not faithful reflection. Okay. So this is the EQ, and I just demonstrated the effect of EQ, and you can apply this kind of, filter on every sound you want. Yeah, and create different effects. Okay, so another EQ. So we talk about this graphic EQ, filter, curve, and there's also shelf filter. So shelf filter is basically low pass and high pass filters. So let's see low shelf. Again, I'm using this white noise. It's the best study material. And let me apply this shelf. Low shelf. So my cutoff frequency is 1000 and amount is -5. Maybe, what about this one? Okay. I mean, you can just experiment with it by yourself. Okay. Not a good. Okay. Let me see. I'll cut off at 16 bits, so it's pretty large actually. My cutoff frequency is 1000. It's low shelf. Let me apply this, and maybe listen to this. Okay, and let me go to analyze plot spectrogram. Okay, so you can see at 1000 hertz, my my filter starts to cut off, right? And then when it's kind of continuously increasingly sloped cut off, and here it starts to be flat. And this level, from here to here, this should be 16 dB, because I choose, right, my parameter to be 16 dB, means starting from my cutoff frequency, everything larger than 1000, they should be cut off by 16 dB. Okay. So I can make this larger and cut more. Let's say we cut 60 dB. And with the cutoff frequency, we want this to be smaller, maybe 659. Okay, apply this. Oh, okay. So from like 6, so I choose 659, right? So from here, it starts cutting off, but it starts cutting off pretty early, and cuts off 60 dB. Interesting. So yeah, I don't know why it's happening. But it's also a way to create interesting sound effects. Okay, using different filters. So shelf filter includes low shelf and high shelf. So low shelf is a low pass filter, right? Cuts off high frequencies. I mean, resume this to, it's difficult to resume. And let's say we try this high shelf. Amount maybe 14. Let's apply this. Listen to this. Oh, so you can tell that, right? A lot of high frequencies are presented there. Right, so this is the high shelf. High shelf is a high pass filter which cuts off the low frequencies. So nearly like 1000 or so, I start to cut off my low frequencies by 14 dBs. Okay, so all my lower frequencies are kind of attenuated, and all my higher frequencies actually boomed up. So these are the high pass and low pass filters that we just experimented. Okay, so maybe let me try, because we used the different noises, right? Pink noise and brown noise, they are all reserving the low frequencies but cutting off high frequencies. So we try to use low frequency to modulate the voice, but here I want to use this high frequency sound. Okay, the high frequency noise was created. Okay, so use this thing to modulate my sound, see what kind of vocoder effect it will give us. Okay, we apply this and see. So maybe this frequency is too high, and it doesn't really overlap with my voice range, so it doesn't really create something very interesting, but still okay. I mean, my suggestion for you to do homework, maybe to find something, some sound, I mean, instruments or voice or noise or whatever sound that probably in the same kind of frequency range as your original voice recording. And then I think it might amplify, certain kind of modulating effects there. if they are in the kind of similar frequency bands. But I didn't experiment this. Yeah. But this is my suggestion and my assumption. Yeah, I mean, you can just try it out if you're interested in this. Okay. So we talked about EQ and filter and noise removal. And there's some, I think I will also briefly talk about delay, reverb, and some wah-wah effects, invert, repeat, reverse. Okay, so I think maybe we can take a break and then we can come back and I will finish with all those left a few effects and we can continue with our next topic. Okay, so we'll take 15 minutes break and we will come back at maybe 45. Okay, 47. 3:47.